Vectors and force. Two completely unrelated concepts at first glance, but when you look at it deeper, every force is composed of vectors. And we're going to learn how to analyze that in today's video, so we can set up how to do problems harder than these. Because if you're missing this basic skill, then it's going to be quite hard to do problems that involve splitting forces into vectors. So let's get started on vector pulling problems regarding force and how to analyze vectors through the lens of force. First, let's start with an example where, suppose I'm over here and I'm pulling on a block with the rope, okay? But then one of my friends, he's also pulling on the rope of the block, but on another side. So we're both pulling it in different directions, okay? So how would I know which direction this block is going to go? And how would I find out what the total force, or using Newton's second law, what even the mass of the block might be? I'm going to show you how. Let's draw the free body diagram acting on this block. The dot for the block itself, right? And then the block of mass something. I don't know what the mass is here. And then what is the force that's pulling on me here? I'm using applied force, right? But that's me. I am using the applied force to pull it. What is pulling on the block itself? The force of tension, right? Because I'm applying the force, and then tension is compacting the rope to pull it that way as well. So I'll call this tension. Now if I draw my friend's rope in red, then we also have another tension here, right? Because he's also using tension. He's also using the rope, which is also, compacting with the mass and trying to pull it. He uses applied force, but the tension force is what actually pulls the block. So this one here would be tension as well. I'm going to label it as tension 2, okay? Because we have two tensions. It's kind of easy to get confused, right? Tension 2 is my friend on the right side here, and tension 1 is me. So how do I cancel out these force vectors, or how do I understand where the block is actually going to move? First, I need to understand that if my friend is pulling in a different direction and I'm pulling in a different direction, the forces are going to cancel out to some extent, right? There might be leftover force, depends on who's pulling harder, but to some extent, the forces are going to cancel out. And we're going to learn how to analyze that. If you remember any vector, right? So, any vector is made of two components. Vectors x component and the vectors y component, right? And then if this is, let's just say this is 30 degrees angle here, okay? And then this is a 45 degrees angle with horizontal. Then you have to you remember how we can split this vector, right? How we can find out the vy and vx components. Vy is just going to be t2 times sine of 30, right? If you didn't understand what I did there, watch my other videos regarding vectors. 30 degrees. And vx here is going to be t2 times cosine of 30 degrees. Alright? What about t over here? T1. Well, same thing here. T1 times cosine of 45 degrees is going to be equal to Vx. And T1 times sine of 45 degrees is going to be equal to Vy. Okay? So to some extent, I have to understand how the Vx and Vx on both sides are going to cancel out, right? And let me show you how. So if I was to take, let's just say right is the positive direction, okay? In general, that's what the consensus is. Then Vx, so I'm going to depict this as T2x because it's the x component of T2. It's going to be in the positive direction. And you're going to subtract which vector? t1ets, right? Because it's in the opposite direction. And remember, you can't subtract vectors themselves. You can only subtract x and y components of the vectors. So you do that. And then what's this going to give you? Your net force in the x direction, right? Because there's no other force in the x direction. No frictionless, right? It's just frictionless force. So there's no other force, which means these two forces may constitute your entire x forces, right? So if you cancel these out to some extent, they're just going to give you the net f x, right? Same thing for the y's, but in this case, the y's are both going up, right? Which is the positive direction. So t2y plus t1y is equal to net force y. Okay? Makes pretty much, like, it makes a decent amount of sense, right? And then if you want to find the acceleration of the block, what do we need to do? So if you have force x vector here, and a force y vector here, the total force y vector, right? How much is going up? The force x vector, which could be this way or this way, but how do we find the magnitude of the vector? We just do this, right? We have to square both of these terms, fx and fy, and then take the square root of that. And we get the magnitude of net force, the total net force, right? Because these are net force in the y and x directions. But if you want a net force in the total direction, like the total net force, the magnitude, then we'd use that vector formula to find that. And then you could use arctangent over fy over fx to find the angle here, right? Basic vector math. So let me show you an example of how this would work out, okay? A block is pulled two ways, okay? Frictionless floor, so no friction here. Rope 1, so this is tension 1 here, is 40 newtons at 30 degrees. Oh, whoops. This other one would be tension 1. Because this is the 40 newtons at 30 degrees, right? Rope 2 is 25 newtons at 50 degrees left. Okay, so 50 degrees left. And then what do we need to find? I want to find the acceleration of the block, okay? How am I going to find that? I'm going to split this into components. So net force x is equal to tension 1x plus tension 2x. The signs I'll change up later, but we know that these two forces constitute the x movement, right, of the block. So I have to add these forces in some way to get the net force in the x direction. So what is tension 1x? Tension 1 is this block here, which I'm going to denote in red. And we know that's going to be equal to, so the magnitude is 40 newtons. 40 newtons times, what is the x component? Cosine of 30 degrees. Right? And then what is the y component here? The tension 2's x component. That's going to be plus 50 or 25 newtons times cosine of 50 degrees. Which is going to give you this x vector here. And how exactly are you going to swap the signs here? Well, it depends on what you define as positive and negative, right? But let's just say that right is positive and left is negative. You don't even need to say that. You can just say they're in opposite directions, so I'm going to subtract them. But let's just say this for the sake of simplicity. So then we know that instead of plus, this would be minus, right? Because this x force is going the opposite direction. So this is going to give you, you're going to have to pull out your calculator to do some math here. 40 times cosine of 30 minus 25 times cosine 50 to get around 18.57 newtons. Okay, this is net force in the x direction. So I'm going to erase all of this so we can just have more space here. 18.57 newtons. Now I need to do the same thing but in the y direction. So let me make separate space for myself here. net force in the y direction is going to be equal to tension 1y plus tension 2y. And then do we need to swap the signs? If I define up as positive, then both vectors are going up, right? They might be going in left and right, which is opposing x vectors, but both vectors have positive y components. This is going to be equal to tension 1y is just 40 newtons times sine of 30 plus tension 2y is 25 newtons times sine of 50. And if you add those, you should get, so 40 times sine of 30 plus 25 times sine of 50. This should give you approximately 39.15 newtons in the y direction. So I can raise all of this. And over here I can write 39.15 newtons. Okay. How do I find the acceleration? So this is net force y here, and this is net force x. Net force total is going to be the magnitude of both of these vectors, right? So imagine that, so since this is positive, because if this is negative, that means we're going left, right? So I know this is going to be positive here. 18.57 newtons. And we have 39.15 newtons. So obviously, very not to scale, right? This doesn't make sense here. The scale is just don't mind it. Then the magnitude of this vector here, or the total vector, the like final vector, right, is going to be square root of the x vector, which is force x, net force x, right? And I'm just going to square that, plus force y, or net force y, squared. So if you square 18.57 newtons squared plus 39.15 newtons squared, what are you going to get? You're going to get, so 18.57 squared plus 39.15 squared, and then take the square root of that, which give you around 43.33 newtons. And this is going to be the total net force, okay, because that's the magnitude of this force vector, the total vector. If there was a bit confusing what I did there, just remember that the magnitude of this vector, right? So in that force, just force squared, it's going to be equal to these two vectors squared plus each other because of Pythagorean theorem, as well as just basic vector math, okay? If it's a bit confusing, I advise you to refresh on vectors and look at my other videos on that. Okay, so now what do we know according to Newton's second law? Net force is equal to mass times acceleration, right? Since mass is 6 kgs, 43.33 newtons is equal to 6 kgs times acceleration. So acceleration is equal to 43.33 divided by 6, or 7.22 meter per second squared. Pretty neat, right? And what's going to be the direction here? The direction is just going to be the arctangent of force y over force x, right? It's the y component over the s component. Basic vector math. So it's going to be 39.15 over 18.57. The newtons cancel out, but I'll just put them for just in case. And then that angle there should give you 39.15 over 18.57. That's approximately 64.62 degrees. Okay? And since there's no tricks here, because if the vector is positive right and up, then this 64 matches up, right? If the vector was down here, we'd get the same 64 answer, and we know we need to add 180 here, right? But we know the vector is just here, so it matches up. It's good. Now let's try a different problem. Okay, so that's when tension was pulling on, when it was tension, okay, regarding blocks. But now let's look at a car and see how the car accelerates here. A 1200 kg car, okay, and a tow truck at 2000 newtons at 10 degrees. So this is 10 degrees here. So a tow truck is towing it at that angle. And a 3-winch rope, 1500 newtons at 35 degrees. And both of them are on the same side. So if I was to break up these vectors here, I would get, so here, this vector, x component, y component, x component, y component. They're both in the same direction, right? Y is both upwards and x is both rightwards. So they're both going to be adding each other. There's no opposites here. It's because if right is positive, they're both going in positive, and if up is positive, both are going in positive. So let me erase that. Draw back my angles. 10 degrees, 35 degrees. Okay, so let's find the force, the total force, and then let's find the acceleration of the car, as well as the angle of acceleration of the car. The net force, the angle of the net force, yeah. So net force S is going to be 1500 newtons times cosine of 35 degrees plus 2000 newtons times cosine of 10 degrees, because they're both in the same direction, right? So this should give you around 3,198.34 newtons approximately. Okay, so yeah, around 3. This should be, I mean, this is what I directly plugged in, and this is what I got. You might have got a different answer if you, so over here, right? Obviously our answers aren't matching up, but it's only by a few decimal points. So I'm assuming we might have rounded differently and then added when I was making the question. Anyway, so this is good, right? So, and then we know that's net force S. So what's net force Y, which I'm going to do over here. Same thing, but the signs of both of them, and they're both in the same direction, so I'm going to add them. 1500 sine 35 degrees plus 2000 sine 10 degrees, right? And it's going to be, so I'm directly plugging it in here without rounding. So if you're rounding, you might get a different answer than I did. And I got 1,207.66 newtons. Okay, so net force, just in total, right? Net force total is going to be the square root of 3198.34 squared plus 1207.66 squared, which is going to be, so let me do that. And we have to take the square root, right? Because Pythagorean theorem is c squared is equal to a squared plus b squared. But then to find c, you have to take the square root of a squared plus b squared. So this is giving me around 3418.75 newtons. Okay, which is pretty neat. Nice answer. And then net force is equal to m times a. So 3418.75 is equal to, we know the mass is 1200 kgs. And always remember, right, this has to be in kgs. If I gave you something in grams here, you can make a very easy mistake, because newtons are in kg meter per second squared. You can't have a gram meter per second squared in newtons. So that times A. And then A is going to be equal to 3418.75 divided by 1200. And I'm not including my units here because I know my units are going to be meter per second squared, or approximately 2.85 meter per second squared. Okay. And the angle, I can just do the arctangent of force Y, net force Y, which is 1207.66 over 3198.34. And I get, so if you get a different answer, you always want to make sure. I mean, if you plug in, you only get one answer, but there could be, the angle could be referencing the different thing, right? Because arctangent domain is just negative pi over 2, pi over 2. But there are other angles here that fit that, because arctangent needs to be a function. So this should give me around 20.69 degrees. And since I know that both my net force x is in this direction, rightward, and y is also in this direction, upward, this makes sense, right? If I was down here, I would get the same 20.64, which wouldn't make sense because I'd be down here, and I'd have to add 180. So let's try some practice here. Okay. Rope A, so a big one, a 5 kg block is on a frictionless table. Rope A is 60 newtons at 20 degrees above the horizontal. And rope B is 35 degrees above the horizontal. 35. So net force X and net force Y is what we want to find. Net force X. So what are they both in the same direction? Think about it. Are they? They are, right? Because both of them are pointing up and rightward. So I'm just going to add the forces here. And I count rightward to be positive, so my net force is going to be positive. Net force X is equal to, what is the magnitude of rope A? 60. 60 newtons times cosine of 20 degrees plus 35 newtons times cosine of 35 degrees, which is going to give me, so 60 cosine 20 plus 35 cosine 35. And I'm getting around 85.05 newtons. Okay, so let me erase all of this. And 85.05 newtons. Now net force Y is the same thing, but now I'm going to add the signs. And they're both upward, rightward and upward, so same signs, right? There's no opposing directions here. So 60 times sine of 20, 60 newtons, plus 35 newtons times sine of 35. Okay. And this should give me around, always make sure your calculator is in degrees, right? I mean, not always, but in this case, we're using degrees. Okay, so this is around 40.596. If I round up, that should just give me 40.6. Okay, 40.6 newtons. So net force Y is 40.6 newtons. And then find the net force magnitude. So total net force is going to be equal to the square root of Fx squared net force H squared plus net force Fy squared. So I squared this one, I square the other one, okay? I add them, and then I take the square root of that. And I get around 94.24 newtons. So that's my total net force. Okay, that's the net force. That's the magnitude of my total net force. Find the acceleration. Well, that's just going to be net force, or so my total net force here, is equal to mass times acceleration, or here 5 kgs, times acceleration. Acceleration is just equal to 94.24 divided by 5. So I'm getting 18.85 approximately meter per second squared. And then the last question, find the angle of the acceleration above the horizontal, so the angle of the total net force, which is 94.24 newtons, right? That's just going to be the arctangent of Fy, which is 40.6 newtons, divided by the arctangent of, not just the arctangent, just Fx, which in this case is 85.05 newtons. Newtons cancel out. Arctangent of 40.6 divided by 85.05 is 25.52 degrees. Okay? And since we know that both the vectors here are in rightward and upward direction, our final vector is also going to be upward and rightward. So 25.52 makes sense. I mean, even if you had a vector here, it would still give us 25.52 because of arctangent domain restrictions. Then we'd have to add 180 here. Otherwise, we're good. Okay, so pretty neat here. Then I'm just going to raise this here. Alright, a single rope pulls a 10 kg crate at an angle. Friction resists with 30 newtons. How large must the rope's horizontal component be just to start it moving? Okay, so basically, we have a block here on a floor with friction, okay, so a rough surface. And then I'm pulling the 10 kg crate with an angle here, okay? So I don't want to draw that thing here, but there's the rope here, and there's tension. And then there is going to be an angle here, right? Theta. But I'm pulling at an angle. So I'm going to start over here. And how large must the rope be? How large must the rope's horizontal component be just to start it moving? Okay. So we know in order for it to start moving, the force has to be greater, the force applied has to be greater than F static mass, right? Because static can match your force applied, but the mass static is a mass. And then if your force applied is greater than that, that means your block is going to start moving. It's going to have no static friction. So what is force? What is the formula for static mass? If you remember, that was, so force friction static mass is the coefficient of friction, kinetic friction, okay? Kinetic friction times normal force. And then we don't need that right now. So we could find the coefficient of kinetic friction because they're saying it resists with 30 newtons. But I was just showing you so you understand, okay, for future problems, how you'd solve it if you weren't given the friction here. But in this case you were, so rejoice. Friction is resisting with 30 newtons. And it's always going to be opposite the direction of motion, right? So if I'm pulling this way, friction is going to be resisting this way. So how large must the rope's horizontal component be just to start it moving? So friction is 30 newtons in the horizontal, right? It doesn't matter what my vertical is. I have to counteract friction. How am I going to do that? My horizontal component or tension times cosine of theta, has to be greater than 30 newtons. Okay? Because that's when it matches the friction and then moves it in the other direction. If the vector is just large enough to move it in the other direction. And since there are only x forces here, they only work with each other, not the y force. Okay, so it has to be greater than 30 newtons. Why can a steeper pulling angle give less horizontal acceleration even when the rope tension is larger? Okay, so if you had something like this, theta, if your tension magnitude was larger, why does it give a less horizontal acceleration even when the rope tension is larger? Well, if you think about it, you know that every vector is made of two other vectors, right? Force y, vector y, and vector x here. Vector x is a horizontal component. And if the steeper pulling angle gives less horizontal acceleration, that's because on a unit circle, your cosine is largest when you have a small angle, right? That's when it's largest. The slower you get bigger angles, the lesser your cosine is going to become. So that's why the steeper you get, your cosine is going to become lesser. And then the tension times the cosine of that angle is subsequently, because cosine is lesser, this is also going to become lesser, right? And that's why. So it depends, right? You want to look at what you're pulling at. It might benefit you to pull it at an angle rather than with more force, or it could benefit you to move the angle around or pull it with more force. So that's all we have for now, right? And then with these tools, you guys can work with a lot of different kind of force problems, okay? These are just essential tools you need. Next video, we'll be going over either attwood machines or incline ramps, as well as how to use those. And subsequently, we'll be going over pulleys, dual ramp pulleys, and all such things, okay? So if you had fun, and if you believe I helped you, give me a like and subscribe so I can help others as well and continue my content. Thank you for listening.